everyone. My name is Shahir, and I am a technology officer at the University of Toronto Design League. Oh no,
I think you cut out.
Kyle, can you hear me?
Yep, I can hear you now.
Yeah.
All right, go ahead, Kyle. Tell them
Uh,
about UTDL.
oh, I'm sorry, I didn't hear the first portion. I think you cut out for me at least.
Oh
Um,
no.
yeah, so I'm Kyle. Thank you. I'm the University of Toronto Design League Technology Director. So here at UTDL, the tech team, we host workshops through CAD, analysis, simulation, 3D printing, Arduino. Um, we're all about going from the digital workspace into the physical workspace, getting that first idea and ideation across, getting it into a digital workspace, so you actually be able to see it and prototype it, and then go through and get it 3D printed and get it into the physical workspace and adding electrical components through Arduino to make it functioning and move. We want to help you in the real world at school with all these workshops and to help your information with your knowledge in these workshops for the Designathon, which we'll be hosting in the beginning-ish of February. Stay posted for that. Everything will be notifying you on our social medias and on our website. These workshops are recorded and will be posted on our YouTube channel, utdl.tech, and made available on our website. Shahir, back to you. Oh, I think we have lost you here. Nope, he's joining back in now. Shahir? Sorry for the technical difficulties. It seems he's just having a network issue at the moment. Shahir, are you able to hear us? Are you there?
Am I here? Can you
There
guys
we
hear
go.
me?
Can hear you. Welcome
Oh
back.
my God, I don't know what's going on with my connection. My last resort is going on my phone data,
Oh, wow.
but hopefully it doesn't have to get to that.
All right. Well, thank you everyone for coming. And Shahir, I'll pass it back to you. Shahir, are you able to share your screen?
Yeah, can you hear me now?
Yep, can hear you.
Okay, perfect. Okay. Let's do this.
There we go.
All right.
I can see your screen. Perfect. Thank you.
So the purpose of this workshop is to provide you guys the foundation on how you can perform your own simulations for your engineering design projects. Everything good on my end so far? You guys can hear me, right?
Yep.
Hello, hello.
I can see your screen.
All right.
Thank
I'm
you.
just gonna try and make sure, like periodically, just in case, because I won't really know. Um, so this is really important, performing simulations for your engineering design project. This is prevalent today because of, COVID-19 happening and, future engineering design projects or engineering projects that are happening now are being performed digitally with teammates, working together while they're sitting at their home halfway across the globe. So performing simulations is a great way of providing some useful evidence or some useful information to your client or to your professor, and to overall just have a more complete, more efficient design. So in this workshop, I'm going to be going over, firstly, the motivation behind CAD and simulations. This is a summary slash recap of what we went over last time in our Space Clean workshop. Then I'm going to go and open up Workbench and go over the basics of that program. Then we're going to go look into 3 specific modules. The first one being static structural, then steady state thermal, which will be the third one actually, and then explicit dynamics or non-static structural or non-static simulations. After that, I'm going to hand it over to you guys to practice your own static structural model on Workbench and SpaceClaim, and then we'll wrap it up with a couple of questions at the end. Okay. If Kyle hasn't already mentioned this already, this workshop is going to take about an hour and 15 to about an hour and 30 minutes, maybe even less than that, but we'll see. So the motivation behind CAD, as you can see here, this is what you would call the engineering design process, with the middle being the project space. We went over this last time. This project space is where you and your team will spend most of your time thinking of and working on your project. For the sake of argument, and for the sake of this workshop, I'm going to argue that the testing phase is the most arduous, the longest phase to get past, because when you're building prototypes, you might be wasting your time and energy repeatedly making new prototypes over and over and over again, only to get like slightly different results each time. This process can be sped up by incorporating CAD design into your projects. With CAD design, you can reiterate over a program, and you can overall get a better design and a better first prototype. Last time I went over how you can use ANSYS or just simulations in general to perform heat transfer analysis, impact analysis, fluid dynamics, static structural dynamics, harmonics, and even more to provide a complete picture of your product. And in general, CAD can offer increased productivity, improve designs, save time, save money, simplify sharing with people who are sitting across from each other around the world. And it can save your sanity, with the asterisk being that if you are not proficient in a CAD program, whether it be SolidWorks or ANSYS, you might be pulling out even more hairs because of all the the things you have to know from those programs. So just to quickly go over how you can download ANSYS. ANSYS is a free program for everyone to use. You just have to follow the link above, which will also be provided in the aid sheet, which I'll be giving out in a couple of minutes. You just go and head to the link, click on ANSYS Student, check your system and browser requirements, and then go ahead and download ANSYS. If you are on ECF computers right now, you can go ahead and type in Workbench, on it, and you can load up ANSYS right there. I recommend you guys all open up your ECF computers. I didn't mention this in the beginning, but I'd recommend you all open up your ECF computers right now and have Workbench open because we will be performing the exercise later in the workshop. All right, so let's go into the basics of ANSYS and showcase some simulations that we can do. Okay. So when you first open up ANSYS, you will be met with a page similar to this. On the left-hand side, you will have your analysis modules. This is all this showcases all the different simulations that you can perform. And in the middle right here is where you'll have all your, where you can like set all your modules and just mess around with them. This isn't the simulation space. This is kind of like your hub where you can store all your models and simulations and just have it as like one network, so to say. You can see here that this is a standalone module that can be drag and dropped from here. I'll be showcasing it in a bit, but you can see that it has certain steps right here. And then you can see right here that you can also link the data between two modules by clicking and dragging between them. So just jumping into the program right here, let me see if I can start a new share. Okay. Hopefully you guys can see that right now. This is my Workbench page. And you can see I've already preset some modules already. And these are the three modules that we'll be going over: static structural, explicit dynamics, and steady state thermal. To showcase how you enter a module, I'm going to go ahead and just delete this quickly. All right, it's gone. And say if I wanted to perform a static structural simulation, I would go ahead down to my analysis systems and look for the static structural module, and click and drag into any of these slots right here where it says I can create a standalone system. I'm just going to go ahead and click it. I'll drop it right below here, and there it is. Now, to perform a simulation or to perform any type of analyses on ANSYS, you have to follow a sort of set of general steps. Okay, and these steps are provided in your H sheet, which I will provide right now. So if I go to the chat, just pause my sharing for a bit. Chat file. There we go. I think I sent the workbench H sheet to you guys in the chat. You guys can open it up and see for yourself. And the H sheet will also be provided in an email blast after the presentation. So in your H sheet, you're going to see in the going through a module section that there are these sort of predefined steps that you have to follow no matter the module. And that is, firstly, you define the material, you create the model, then you mesh the model, you apply loads and boundary conditions, and lastly, you solve and view your results. You can see in the bottom right of each square that I've made, the corresponding program slash, you know.
Hello?
Yeah.
Currently we see your file explorer. I'm not sure if that, okay, now it's good. Maybe it was lagging or maybe it was on my end, sorry.
I just started screen sharing a bit, yeah. But right now, what we're going over is just the H sheet, what's on the H sheet right now. But yeah, thank you for letting me know. So let's see. So you can see that there's the corresponding program is attached to the bottom right of each module. So for example, in defining the material, you can see that there is the engineering data program. So just for demonstration's sake, I'm going to go over how to perform a static structural simulation. So just like in the HT, it says to go and define the material, we do that by going through by clicking on engineering data or double clicking it. Now this module, this program can be a bit overwhelming at first, but you know, you have some aid in the HT where you can go over what each of these boxes mean, and I'll be going over them right now. So the most important boxes you'll need when looking at your engineer, when trying to define a material, is this box right here, which is engineering data or D2, and then down here, which lists the properties of a certain material. ANSYS provides a structural steel as the default material property. You don't have to do anything; it's already there. If you want to add a new material into your, I guess your work belt or your arsenal, you would go ahead to this top left corner right here, called Engineering Data Sources. Click it once, and you'll be sent to a sort of different page, where this top box is replaced by various libraries you can choose. And when you go into a library, if I just click it once, or double click it, the materials that are found inside of it can be found right here. And then you can just scroll through and you can see all these different types of materials, ranging from wood to plastics, carbon steel, bronze. These are very general materials in this library. You can find different materials in different libraries. For this presentation, I'm going to go ahead and choose oak wood, because why not? So I'm just going to click on that plus button right here to add. And after that whole box refreshes, I just got to click off of Engineering Data Sources. And my oak wood ends up in my arsenal. If I click on it once, you can see that the material properties of oak wood are listed down right here, where you can see that some give a constant value, while some give a tabulated value. If I were to click on table, let's say for the tensile yield strength right here, click on table, the table actually comes up in this top right corner. This top right corner is where you will be seeing all your tabulated data, and this bottom left corner is where you'll be, bottom right corner is where you'll be seeing the data on the table but graphed. Because there's only one table point, you're only going to see one graph point. Now, say you don't want to use the ANSYS library to find your material. Say you want to make your own material. I want to make my own material and call it, I don't know, blue. Okay, well, blue's been made, but there are no material properties attached to it. If I want to attach a material property to it, let's say Poisson's ratio or just some isotropic elasticity, I can go to the left toolbox right here. This whole left-hand side has a variety of material properties that I can just drag and drop from and just apply it to my model. So I have this blue selected, I have isotropic elastic selected, and I think if I double click, it will be applied to my material. And now you can see that there's some highlighted bits that I have to click on, and I think ANSYS froze over a bit, but then just have to click on and just type in whatever I want. Set this to megapascals. That is very small. Whatever. That is very big. Hold on. There. Okay. And Poisson's ratio, you can just set it to something like 0.2 or something. And then you can add more material properties as you see fit. That's about it for engineering data. Once again, you just start off with your basic arsenal here. If you want to add more materials, you go into engineering data sources, pick out your material, and you can review the properties here, tabulated data here, and graphed data here. Okay. Once you are done with engineering data or picking out your material properties, you just gotta click the X button right here, and you'll be brought back to the project page. Once you're done with a certain section of your module, you'll see a check mark appear on the right side. That means that you've performed everything you need to do properly, and you're ready to move on to the next step. The next step is, like it says in the H sheet, is to create your model. And to do that, you can, if you double click the geometry tab, you will actually open up SpaceClaim, where you can go ahead and model whatever you want, and it will be saved into that module. However, I have a model that I want to showcase to you guys. And to do that, I'm just going to import by right-clicking and clicking on import. And it's already here, but you can go ahead and click browse and just search up the SpaceClaim file for yourself. But I have the model right here. I'm just going to click on static model. And look, as you can see, check mark appear. I'm just going to go into SpaceClaim and just showcase what the model is. And from there, we'll move forward. Let's SpaceClaim open up for a second. It takes a while. That's kind of the annoying part of Workbench, where you have all these different programs working together. Having to open them up each individually is kind of a pain. Okay, but this is just a rectangular prism. No, it's not. It is actually a door. Why did I model a door? Because I wanted to showcase a sort of generic situation that you may apply static simulations to, and might be useful for your everyday life. So imagine this door is in your way and it's locked, and you can't go around it, and you have to go through it because there is something that you want on the other side. Let's say, I don't know, your phone, your treasure, or whatever. Okay, and you don't have the key. As you can see here, I specifically did not model a keyhole, so you can't use a key to get in. And this is an assembly, so that doorknob doesn't move as well. So this door is basically non-functional. It's kind of just stuck in the wall. How would you get through? My first idea was to just press against it, press very hard against it until it breaks. And when it breaks, I'll be able to go through. So I want to use ANSYS simulations to figure out how much force would I need for this door to break. And that is definitely possible. The first step, though, is of course creating the model. But an important part in creating the model is that you want to simplify the model so that it only fits the context of your situation. Okay, because the bigger model you have, the more complex model you have, the longer it will take ANSYS to calculate the result for it. So if you want to save your time, you would want to have a much simpler model. In my case, I'm not going to be pressing against the entire door. Rather, I'm going to be pressing against this single section of the door, and I'm going to be trying to break this part. And in my mind, once I break this part, I've basically broken through the entire door. I know that if I press my hand against this part of the door or the hinges or whatever probably isn't going to feel much stress. I'm only trying to break here. So what I've done is that I've separated the door and what I call the sweet spot into two different solid objects. And when I go and right click the door, I have it suppressed for physics. What this does is that it ensures that the remaining part of the door does not show up in my simulations once I get to that step. And as an extra step, I can choose to just hide it altogether. So now I just have the sweet spot. Before heading off into the simulations portion, one important part to check on SpaceClaim is your topology, or in other words, the surfaces that are in contact with each other. You can check that by clicking on the overall structure tree right here and going down to properties and looking at shared topology. Here, I want to make sure that my shared topology is none, because in this case, the door doesn't really exist. But if you have models where you have different connecting parts or touching parts, you would want to change the topology to depending on what you want to either merge or share. 1 second. So the difference between having none or having merge or share is that if you have merge or share enabled, those topologies will be the two bodies will basically somewhat merge, and in the later step, when you create a mesh, the mesh will be combined between the two objects rather than staying separate between the two of them. So depending on your project, depending on your application, this might be important for you. Okay, so once you're done with your model, you can just click X. SpaceClaim already saves the model into the module. And you can go ahead and go into the model section. Now this takes even longer to load, so just sit back for a bit. Yeah, it's taking a while. If you want to figure out, if you don't want to just keep staring at this, you can also go and check the bottom left where it says starting mechanical. Just so you know that Workbench is, working on opening the program. Okay, now it's loaded up. So just like how in a Workbench module, we were going sort of down the list, engineering, data, geometry, and model, we're also going to be going down the list over here, specifically this part right here, to complete our simulation. This is common across any sort of simulation that you do. So the first thing they want to check is to see if your geometry made it in one piece. You can see that only the sweet spot got transferred over and the remainder of the door did not. So that's good. What you also want to do is once you have your geometry and your object selected, you go down to your details tab and you assign your material. Here you can see that the default assignment is structural steel, but I want my door to be made out of oak wood because I actually want to break it down. So now that that's been done, I can move, you can see the little check mark being done here, and that's all good. Materials isn't really important. It just lists all the materials that you have in your engineering data. You don't really need to look at that. And you don't really need to look at coordinate systems as well. This is just looking at the global coordinate system or whatever extra coordinate systems you may have inserted in your SpaceClaim model. The next important part, which is also in your H sheet, is the mesh step. Now, to perform a mesh or to complete a mesh, what you have to do, there's a fire truck outside, I'm sorry, is you just have to click on mesh once, right click, press insert, and you first want to insert a sizing of your mesh. Okay, I'll explain a bit more what a mesh is once we actually create it, because it's a bit easier to explain when it's done visually. So the first thing you want to do always is to insert your sizing. And you can see that there are two highlights that I have to fill out. The first one being geometry. So what I have to do is I have to go to my selection tools right here. I'm going to have to select my body. So I'm going to use the body select tool, select my body, and then apply it. So now the mesh is applied to that. And ANSYS sets a default size of, depending on the size of your model, it's going to send a default mesh size. You can change it to whatever you want. I'm just going to set it as 2 millimeters. Doesn't really matter for me. But in general, if you want a more accurate result, you would want a more smaller, more finer mesh. If you don't care for the result of a specific component or a specific part, then you can go ahead and go for a larger mesh. Next, under mesh, you're going to have to go and insert a method. Once again, just body select and click apply. And you can change the method of your mesh or the shape of what your mesh is going to be by going to method and selecting between all these different options right here. I'm just going to go ahead and stick with automatic, but other mesh options that you can use that could lead to more accurate results is hexagon and tetrahedrons. These sort of the main ones that you can use, but you can also use the following right here. By using the automatic mesh, because this is a rectangular prism, I'm probably going to get like a square mesh because that's the most simple, probably the most accurate for this situation. So to actually generate your mesh, all you have to do is right-click your mesh once again, and instead of going to Insert, you're going to go down to Generate Mesh. And you can see that ANSYS is working on it pretty quickly right here because it's a small object, and you can see that the mesh has been made. So what is a mesh? Basically, a mesh is made up of nodes and elements. Nodes being these sort of like these edge points right here, and elements being the lines in between them. And to oversimplify what goes on is that a sort of calculation happens on each node. Sorry, an element is the square shape. A sort of calculation happens on each node, and the result is kind of put into a matrix. And each element has its own elemental matrix. In this case, I believe it might be a 4x4 matrix of stress results or strain results or whatever results acting between each of the nodes. And then you just expand that, and you can see that every element has its own matrix, and then there's a huge global matrix which is solved and gives an overall result of which parts of the model, which elements are receiving the most stress, which elements isn't receiving that much stress or strain or whatever. So now that we have our mesh in place, we can go ahead and start setting up our boundary conditions and our loads. To do that, we go down to static structural. You can see here we're following the check marks, and the next thing we have is static structural. What we do is, once again, we right click, press insert, and I'm going to apply a fixed support onto, using the face selection tool, onto the faces while pressing and holding control of my door piece. Because in reality, this door piece is attached to the door. And this isn't supposed to be moving anywhere. So once that's done, just apply that. You can see that the fixed support has been applied on all 4 faces with the coloring. And next, I'm just going to go ahead and apply a pressure on this face right here. I'll do that by pressing insert, and instead of a fixed support, I could have also done displacement or like a frictionless support, or whatever. But I'm going to go ahead up here and apply a pressure right here. It wants me to select my geometry again. I'm going to use face selection, use this face, apply, and apply pressure of let's go with 100 megapascals. I don't know if that's wrong, but for the sake of simulation, we'll just use that. All right, arrow's going in the right way. We are pretty much set. Okay, as you can see here, we are also pretty much set with the array of check marks that you can see. The last step is to call upon your solution, is to tell ANSYS what do you want to see, right? And to do that, you have to right-click solution, press insert, and I want to see my total deformation. I also want to see the max equivalent stress, and I also want to see the equivalent strain. All right, once I have all those set, I will right-click solution once again and press solve. And ANSYS will take a couple seconds to solve the model. All right, you can see that they all have check marks beside them. And that means the simulation has been a success. To see your result, you just click on each one of them, and you can see the deformation that occurred when I pressed against the door with 100 megapascals. You can see the stress. You can see that the stress is especially accumulating on the edges where, the door is like, fixed to the remaining part of the door. And you can see that there is also an equivalent amount of strain happening over there. So this is just one example of how you can perform a simulation on ANSYS. The general steps are more or less the same on any module that you decide to choose to do. I'm going to be moving on to explicit dynamics to showcase how you can perform an explicit dynamic simulation. So I'm not going to make a new module because, as you saw from before, solving could take a while depending on the simulation, and explicit dynamics especially takes a very long time to solve. So I have it already solved, and I'm just going to go over through my steps. As you can see, I have the engineering data linked. How I did that is just I clicked and dragged the engineering data between the two. And if I click on it right here, if it loads, I have to go to the parent engineering data, and you can see that I have my materials right here. Okay, but the geometry is different because for explicit dynamics, as you can see with me pushing it against the door, it didn't really. It seems like it requires a lot of pressure to bust open the door just by simply pressing against it. So for explicit dynamics, I decided to go for a slightly different approach, and you'll see it once it loads up. So as you have seen, let's see if it loads up. So as you have seen in the movies, the most effective way of breaking down a door is by kicking it with your foot, right? In this simulation, in this case, I'm going to be kicking it open with a steel toe boot because that is the most effective thing I can think of right now, okay? Once again, we have our sweet spot, which we're aiming for, and we have, a pretty basic boot that I modeled. This is the end of the boot. Once again, I simplified it because I don't care about my heel or, my ankle. I'm only caring about the very end of the boot that's going to be in contact with the door. So a couple things to make sure when you're setting up a non-static or explicit analysis simulation, or in other words, an impact analysis, is that you want to make sure that the impactor, and I guess the impactee or whatever you're trying to impact, are very, very close together. In the range of 0.1 to 0.5 millimeter range. The reason you want to do that is because the further apart the objects are from each other, and the more you tell ANSYS to make them move, if I had to make the shoe move from like a meter away or something, or like even a centimeter away, the computation time that ANSYS will take to complete the simulation is going to increase exponentially. And you don't want that. You want to have a very quick computational time. Even here, even if it's like a 0.1 millimeter gap, even this takes like at least a minute or like 2 minutes to do, which is why you really want to keep it as close as possible. So yeah, that's basically it. I just wanted to showcase that, what I modeled right here. Because the two objects aren't touching, there is not going to be any shared topology or anything, so we don't need to worry about that. And we can just go ahead and click off. All right, going to our model. I'll let this load. You know what, let me just, once I have this loaded up, I'm gonna load up the remaining two modules just so it's quicker. But yeah. Okay, that is loading up. See if that works. Okay, so this is all loaded up. It's the same sort of general steps to perform the simulation here also, with a couple variations for explicit analysis specifically. Once again, we go to our geometry and we click on both of them to make sure that they've been transferred in properly. And we go ahead and we assign our material down here. In this case, we have the oak wood door and the structural steel boots, right? We can skip materials, skip coordinate systems. You can see a connection portion right here, which is showing 0 body interactions. Connections, this connections tab basically showcases any sort of contacts that are happening between 2 objects or 2 or more objects. Because there's no actual contact going on between the two, we have no body interactions. But you will see one in a bit. The mesh has already been completed. I inserted a body sizing for each object, okay? And I made it automatic method for both. I let ANSYS choose what's the best method to make the mesh. The reason I chose a different body sizing for the 2 materials is because I really only care about the door. I don't care about my toes. I don't care about my shoe. I don't care, what stress accumulates on my boot. If my foot breaks, so be it. I'm just trying to break this door down. And so I'm going to have a more finer mesh on my door so that I can more accurately see when my door fails. Okay, and less accurately see if my foot fails. So once that's done, what you have to do in your explicit dynamics tab is to first set your initial conditions, which can either be a pre-stress, which I listed at 0, and you can also list a velocity, which we have to list because the shoe is, hitting the door with some velocity. Here I went a bit crazy and just I selected the body first of all. That's why it only has the one body selected. And I went ahead and put in a velocity of negative 50,000 millimeters per second, which is, if we change the units in the bottom right here, 50 meters per second. So yeah, a bit fast. Once you have those 2 done, you'll see a check mark, and you can go ahead and fix your analysis settings. So in this case, you may have seen analysis settings in your static model, but I never went over because it didn't really matter. It matters here now because the way you configure your analysis settings will determine how long ANSYS will take in solving the model. So if I just click on analysis settings right here and go down, you'll see a lot of different things, but there are only two things that you need to know. And those 2 things are your end time, meaning how long you plan to perform the simulation for. Here you can see I made it in the range of microseconds. Like this is happening extremely quickly, and I only need to see the stress in that small window of time. Because I have it so small, ANSYS is able to process this fairly quickly. The other thing that I want to look out for in the analysis settings is if I scroll down and go to output controls and look at my resultant number of points, I would like to set it to about 100. Resultant number of points is basically the number of frames you want to see when you're viewing your result. So about 100 frames would be good enough to accurately see it. If you feel like ANSYS is taking way too long to solve your model, then you can go ahead and lower that number. If you want to see more things, then you can increase that number. Okay, once you're done with your analysis settings, you can go ahead and apply your fixed support like always. But in the case of a moving object, you want to apply a displacement to either the entire body or to the faces that or to a face. It doesn't really matter, I think. But you would apply a displacement to the shoe. And what you would do is you would first of all select either the body or all the faces. And then go down here and select which of the 3 axes do you want the object to move freely at. In this case, I selected that the Z component is to be free because the shoe will be going in the Z direction. And I fixed it so that it can't go in the X or Y because we simplified it enough to go in the Z. a note on simplifying your simulations or simplifying your adding assumptions, like the one I just did right now, where I just said that my shoe isn't going to be going in the X or Y direction at all. It's only going to be going straight in the Z direction. This is an assumption that if I were to be, if I were in an engineering design project, I would have to list down somewhere, that I made this kind of assumption, or else your professor or your client might be a bit questioning regarding the results. Okay, you could be a bit more complicated and add your X and Y components, but simulations is able to give sufficient results, even if you simplify it a bit. All right, once you're done that, you have everything else set up. You can go ahead and call upon your solutions by right-clicking, insert. I call upon my deformation, my strain, my stress. They're all right here. And then you can see the results already preloaded right here. Once again, to solve, all you have to do is right-click, and it would show up right here, but you would just right-click and press solve, or it would be up here as well. To see your explicit analysis in action, all you got to do is just press play, and you'll kind of see it going a bit like so. You can increase the frames to up to 100 frames, because I believe that's what you put it on, and you'll see it happening a bit more, like slow motion, and you can see my foot gets a lot of stress, or I believe, or my foot gets some, like the most deformation, while the door doesn't really get much. So a couple questions that you might be asking here is that why isn't this door like splitting apart from the back? Why isn't it like exploding or anything? Well, it's because of the material that I selected. The material that I selected was a general oak wood material with only elastic properties. The material does not have plastic properties or properties that are in the failing region of the stress strain curve. So ANSYS does not know how this material, or how or when this material will fail. And so it can only show the elastic portion of the simulation. If you want to add plasticity or failure conditions to your simulation, you would go into engineering data, and you would manually input that plasticity data either as a table, or I believe you'd have to do it as a table. You'd need a variety of points at different strains for different stresses. Okay. Same story with equivalent stress. You can see nothing really is happening, But that is overall how you can perform an explicit analysis simulation. Yeah. Now that that is done, we can move on to the last module that we're going to be going over before we go into our exercise, and that is steady state thermal. So we've already gone over the first two, engineering data and geometry, so I'm just going to go ahead and skip right over to the model, which did not load, so we have to sit and wait a bit for it to load again. But this model is like separate from the whole door breaking thing from before. This is just a simple model to showcase steady state thermal. It's loading up. All right. And once again, it's the same story. So first of all, this is a simple piping system, which will have heat being applied on the inner walls, and a fin acting as a sort of a piece to sort of like transfer heat away from the pipe, sort of like a heat sink, so to say. So that's just the basic model right there. Once again, check if my geometry made it through. It has. My piping and my fin. They're two separate objects because I want to set my pipe as copper alloy, which I got from the engineering database, and I want my fin to be of aluminum alloy. Okay. Once that is done, you can go down, and connections have something interesting. So you can see that if I just go through the menu of connections, you can see that ANSYS does detect the contact between the piping and the fin. And you can see that the area the areas are highlighted right here, or the faces. I can define the type of contact these two are facing right down here by going by type. Right, by default, ANSYS assumes that it is bonded, meaning that the two objects aren't supposed to move between each other, which is what we're going to be keeping. But if you wanted to have it so that like you want the fin to be, able to move against the aluminum alloy with some sort of friction, you can select that right here. But you would have to enter a frictional coefficient. I'm just going to stick with bonded. Okay. Same story with mesh. You apply a body sizing for each thing. I made the body size, the size of each element to be sort of the same because I want to see the heat flux and the temperature for both objects. And then I also just applied the automatic method for both of them. For applying my boundary conditions and my loads, I once again just go right-click Steady State Thermal and insert, and I have a library of things I can choose from. In this case, I went with convection and heat flow, where with heat flow being the inside of this piping at 150 watts, and my convection being on the faces of the fin with the film coefficient at 2.5 watts per meter square. These numbers are something that you'll have to put in when applying these sort of boundary conditions. So that's just something to keep in mind. Also, you're also able to apply an initial temperature. By default, I believe it is about 22 degrees. You can set it to whatever, 24, room temperature, whatnot. And you can also mess around with your analysis settings right here. But steady state thermal isn't as demanding as explicit analysis, so you don't really need to do much here, to save computational time. Because I had made an edit up here on the connections part, ANSYS is requiring me to solve the model again, which is no problem. But you can see here that I called upon insert thermal temperature and insert thermal total heat flux because I want to see those two things. If I just right click and press solve, it should solve in a quick second. So this error message that I got right here is something to do with the geometry, but because I have my results here pretty successfully, this isn't a very major error. There are some errors that can be that will not allow the simulation to go through, and it will typically tell you what you would have to do by just double clicking and just reading the error, and like you'll know, okay, what went wrong? Was my mesh too fine? Was my temperature too high? Was it like too complex for ANSYS to solve? You'll be able to figure out what's the error, and you'll be able to solve it. So yeah, if I go up here and I just click on solution and just click off the error tab, I can press play, and you can see how the temperature changes over time. And I can also see how the heat flux changes over time. And you can see that there is a good amount of heat flux that goes into the fin, but possibly not enough. And maybe you might another fin right here might be good, for additional cooling of the pipe. Okay, and that is about it for the 3 modules for ANSYS Workbench. Now we will be moving forward, and I'll be handing it off to you guys to work on your own little exercise, which you can find on the screen right here or in your H sheet. The situation is you have this model to first make. You have on SpaceClaim, you would drag and drop the static structural model module, go through the steps, and you would have to make this model and perform the following simulation. Just keep in mind that the material that you'll be using is structural steel, so you won't really have to do anything in the engineering data section. And while you have your results ready, ask yourself the following questions. What is the critical point or the area? Where is the max stress or deformation? And based on your first 2 answers, where would you make improvements on your design? These are key questions that you would be answering in any sort of design project, so it's good to practice it here. I will give you about, let's say, 5 to 10 minutes to work it on your own. And after that, I'm going to start going through the model by myself, starting by making the model and performing the simulation by myself. So if you're stuck anywhere, you can come back to the Zoom call and just watch me do it slowly. So yeah, I'll leave it to you guys. I'll let you guys work on it for about 5 to 6 minutes, and then I'll get started on it by myself. If you have any questions, you can feel free to ask me right now too. Okay, I'll start working on the model slowly. If you're already working on it, then you can continue to do so. I'll just be doing it on my own. So, let's see. Guess I'll just use whatever I have here. Structural steel, that is good. Sorry about that. I live outside of a fire station, so fire trucks are always leaving, coming, going.
Shahir.
Yeah.
So since you're currently working on the model, do we have to do the model in ANSYS Space Claim, or can we do it in another program? Is there an option to like import from another program?
Yes, but it does require a good amount of steps. Okay. So I'm assuming you want to make the model in like say SolidWorks, right? I'm fairly certain that you can open a SolidWorks parts in SpaceClaim and then save it as a SpaceClaim file. So there isn't like explicit importing. Like you could import other SpaceClaim models using where is it? Prepare or where is it? Assembly, sorry. Yeah, so you can import files using, the plus file part, and it can only be, I believe, SpaceClaim files, but you can start with a SolidWorks file, save it as a solid part, and I believe you can open that up in SpaceClaim, and then save that as a SpaceClaim file, and then, import it into Workbench. It's a good amount of steps, but, it's basically easier to just like do it all in SpaceClaim if you want.
Okay, thank you.
Just let's see, for select the space and make the circle. Pretty sure the circle is right here in the middle. That's how I made it. and it's a diameter of 30 millimeters. Oops. Cool. We'll cut it right there. Just gonna select this, get out of my sketching mode. It's gonna be a bit lazy, and 1 second. Just gonna move it over. I believe that's the middle. And just utilize the mirror function to first select my mirror plane and body so that it's all mirrored up. At this point, I don't need the plane anymore. Oops. There. Get rid of all these duplicate planes. Make it 50. Pull that. Cut it, but only by 10. And then sketch on this face once again, right in the middle. Just make a 20 millimeter circle. Just leave it right there because we still have to make the bottom part. Okay, now that that is done, just go ahead and just pull this all the way through. And I believe that is it for the model. The hole down there, and the bracket has been made. Now that I'm done with the model, I can just click off of it. Don't really need to save. ANSYS already has it stored. Check mark done, and I can just go ahead and go into the model. All right, so once the model opens up, I'll do the simulation and I'll discuss the questions that I've listed for you guys. It's showing the old model, but I should update in a second. So Hill, relating to your question about importing ANSYS and SolidWorks files into ANSYS and whatnot, what I found is that while you can import SolidWorks files into ANSYS, you cannot export ANSYS files to SolidWorks. So that's one thing to keep in mind. Yeah.
Okay. Yeah, it would make sense that one can or one would tend to import from SolidWorks to ANSYS to do simulations. So that's good.
Yeah.
Thank you.
Yeah. I will say though that I have found workarounds, being the stubborn guy I am, I have found workarounds to like export ANSYS into SolidWorks in case I want to do something, but a lot of the geometry is lost if it's a complex object. Some faces don't transfer 100%, so it's not very reliable. So it's something to keep in mind.
Thank you.
All right, no problem. So once that's in, I can assign my material to structural steel. I can also do water if I wanted to, but structural steel for now. Use my mesh and I'll body sizing, and it's already been there from before, but I'll just select my geometry, apply, let it do whatever, let it ANSYS select for itself. Use an automatic method. Whoops, select first, apply, and then use an automatic method. And let's generate the mesh. Now, one thing to keep in mind when doing these simulations and when, meshing specifically is that the ANSYS student free version only allows a certain number of nodes / elements that can be, applied onto your object. So once this mesh finishes, I'll let you know exactly how to figure that out, like how many nodes you've made or how many elements you've made. This is taking quite a while. It might be because it's too small of a mesh. See if I can cancel this. Yeah, seems like it was taking a bit too long. So let me just put it in millimeters. Let me just make it 5 millimeters. And there, should be a lot faster now. And there, now it's done. So ANSYS has a limit to how many nodes or elements you can have on a singular mesh. And to see that, how many nodes you have, is you just go to mesh, you go down to details of mesh, and you go all the way down to statistics. And down here, you can see that I have 69,000 nodes. That is not good because ANSYS only limits students to 32,000 nodes / elements, whatever, in between. So just for this sake, I'm gonna quickly apply the fixed supports and just showcase what happens when you have too many nodes. How ANSYS reacts, so to say. So let's do a fixed support on the inner parts of the circles right here. Let's apply the pressure on this face right here. 100 megapascals, is that what I said? No, I said 10. All right, 10 megapascals. Okay, now I already have my 3 things that I want listed. If I press solve, I'm gonna get an error, I believe. There we go. Your product license has numericals problem size limits. Because the limit is 32,000, ANSYS sees that I have, almost 70,000 nodes, 46,000 elements. It's not going to accept it. So I got to increase my mesh even more. Let's make it to like 10, let's say. And generate. Let's see what we have here. See, it's even like the mesh was even more quicker, and now we have a lot less nodes and elements. And so ANSYS should be able to solve it once I click solve, like so. This is at the cost of, lost accuracy, which is something to keep in mind. So you have to play around with it. Maybe try and get a mesh size that's like close to the limit, but not exactly, so you can get the most accurate results possible. So the question is, what is the critical point? Well, we can go into deformation, and well, this doesn't seem like a critical, this might be a critical point, but if we see by playing the simulation, we know the pressure is being applied down here. And we know that this part is just it's reactionary. I would argue that the critical point, if we look at the equivalent stress, it is right there at those corners. If you see, if I press pause, you'll see where those red marks are. Those are the critical points. And by extension, you can see that the max stress and deformation in this case, the max stress is about 120 megapascals, and the max deformation is about 0.17 millimeters. Once again, you can see that because I applied a pressure here, the whole sort of model kind of like deformed downwards. If you want to get a more accurate, more realistic picture, I believe for press stop, there is a method. I am not able to find it right now. Oh, it's gone. But there is a method to see your deformation in true scale, or in 1.5 scale, or whatever you, or however however you want to see it visually. Yeah, I can't really seem to find it right now. Is it this? Right here, yes. You have auto scale and you have true scale, and true scale just basically shows how it would be like in literal real life conditions. You can see that 0.17 millimeters really isn't that much, so it's not really that much deformation. But you can, auto scale typically has it more exaggerated. So to see this, you have to go to result, and then in this tab right here, you would just look at your scale. And yeah, the last question is what design improvements you would make. Personally, I would go ahead and try and add some kind of rib, some kind of ribbing or some kind of support structure on these points right here, maybe like in a triangular shape. So I can extend the support and sort of lessen the deformation down here. This kind of design thinking is really useful for engineering design projects, because look at what we just did. We thought of a new solution without having to create a new prototype, without having to buy new material, make a new model, spend hours on making a new prototype. We did it all in a matter of minutes on ANSYS. So that's why simulations is so useful in our design projects, and which is why it is so important to us nowadays when we're working on problems such as these. That is going to wrap up the end of our workshop. I hope you all have learned a little bit about ANSYS simulations, and I hope you all go out there and delve into the program more on your own time and learn more about it. If you have any questions, I'm sticking around for a couple minutes if you want. But other than that, I wish you all a good evening, and yeah, have a good evening. See you guys later.
Thank you very much, Shahir. Great job. Thank you, everybody, for coming.